So deductive reasoning. We're talking about proofs, which we said were logically valid arguments, and here is our definition. Arguments valid if and only if, so equivalent. It takes a form that is, it's impossible for the premises to be true, and then the conclusion comes up false. There are different types. The one we're most familiar with is simply a direct proof. In Latin, that's known as modus ponens. Here it is set up in our logic notation. Okay. What we're saying is, if we have P and we know P implies Q, so we have those two things. We know P implies Q and we have P, then we must have Q. We were talking about this yesterday, the if-then statement basically. P produces Q. So if we have those two things, if we know P and we know P implies Q, then we can say, well, we've got Q. That's a direct proof. Now I'm going to put it in a truth table here to show that it does not matter whether P or Q are true or false, we will always end up with the true statement. So there's all the possibilities. True, 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 false, false, true, false, false, of course. I'll put those through to all our P's and Q's there. So we work from the inside out of the parentheses. So the P implies Q. Well, we said with that one, the only one that is false would be true implies false. So all the others are true. So now I'll get this blue one and I'll match it up with P here. So we have, there we go. So now the only one that is true is the very first one. Because if we have true and true, it must be true. But all the other ones, I've got false and false, well that can't be true. False and true, well it can't be both. And false and true. So we now have them true, false, false, false. Now that I'm going to match up with the last one. Does true imply true, true imply false, and so on? Well, yes. All of those turn out to be true. So that's telling us that this idea of a direct proof is a logically valid argument. It will always work. Okay. Here, I guess this is where geometry is. We have several statements. We can join them together. So in other words, saying, well, if we know P implies Q, and we know Q implies R, well, then it's fair enough to say P implies R. Because P goes to Q, Q goes to R. Alright, let's do a few. We're going to prove that if a number is odd, then its square is also odd. So I'll start off, well, n, it's going to be an odd integer. So I've got this odd number, n. But how do I force n to be odd? I can define it like this. I'll say, well look, n's going to be 2k plus 1, where k is some integer. That will always create an odd number. I could have just as easily said 2k minus 1, I suppose. That would create an odd integer. Okay. Well, what would n squared then look like? Well, it would be 2k plus 1 squared. If we expand that out, 4k squared plus 4k plus 1, we want to show that this is also odd. So in other words, it's going to be 2 times some integer plus or minus 1. So if I factorise that, I can take out 2 and I get 2 outside of 2k squared plus 2k plus 1. Well, hang on, yes. That 2k squared plus 2k has to be an integer because we define k to be an integer. Well, if we define k to be an integer, well then 2k's got to be 1, k squared's got to be 1. So yeah, it's fair enough to say 2k squared plus 2k is an integer. So it's in the form we like. So hence, yes, if n is odd, well I put a comma, I could have just put then, if then statement. If n is odd, then n squared is also odd. So when you're doing your proofs, when you're setting them out, remember the right hand side of your page, that's where you're putting your explanations, just like you did in geometry. Vertically opposite angles are equal, whatever. So the same sort of idea. Here's one that came from the 2021 HSC. They had to prove that 2 to the power of n plus 3 to the power of n cannot equal 5 to the power of n for every integer bigger than or equal to 2. Cannot happen. Well, 5 to the power of n is equal to 2 plus 3 to the power of n. So I did that because it seemed a logical thing to do. Because we've got 2, we've got 3 and 5, and 2 and 3 is 5. So it's a starting point. But you may recall from our binomial theorem, 2 plus 3 to the power of n, I could rewrite. And I'm going to rewrite that as nc0 2 to the power of n plus nc1. Powers of 2 will go down by 1, powers of 3 go up by 1, and we would keep going until we get to the very last term, which would be ncn 3 to the power of n. Well, that's got to be bigger than 2 to the power of n plus 3 to the power of n, because you've got all those middle terms. Well, it'll always be bigger if n is greater than or equal to 2, because if n was equal to 0, then we'd only have one term there, 0, C0. And if n was equal to 1, we'd only have the term 1C0 and 1C1, the two n1s, and that would be 2 to the power of n plus 3 to the power of n. But as soon as we have more than n equals 2, we're going to have these middle terms, which will increase the value. So, yep, it's good to say that that's going to be greater than, so long as n is bigger than or equal to 2. Well, if it's greater than, it can't be equal to it. A direct proof of that particular one. Prove that the sum of the squares of 5 consecutive integers is divisible by 5. I just put this in a box here. It's a fairly obvious thing, but I'm just stating it here. I know that if p and q are both integers, and that q is divisible by p, then there must be a number such that q is equal to p times n. Because we say p is divisible by, so it goes into exactly and by a whole number. That's the idea I'm going to use here. So I'm going to let q be this sum of the squares of 5 consecutive integers. Now, the trick here to make my life easier for myself, I could have gone n plus 1, n plus 2, n plus 3, n plus 4. But that expansion is going to be huge. What I've done is I've picked the middle number to be n and gone either side of it. So I've got n minus 1 squared, n plus 1 squared, n minus 2 squared, n plus 2 squared. And why do that? Because now when I expand this out, what I know is this first one, the middle term would be minus 2 lots of 2 times n, and that very last one will be plus 2 lots of 2 times n. So all those middle terms in those binomial expansions will cancel out, and I'll just have, in each one of these will produce n squared, so that's why I've got 5n squared, but then this one will have 2 squared, this one will have 1 squared, well that one's naught. Then the next one's 1 squared, and the next one's 2 squared. It saves time on the expansion, basically. So I've ended up with 5n squared plus 10. Remember, we're trying to show that it's divisible by 5. In other words, I can write it as 5 times some integer. Well, I can factorise 5 outside of that. I get n squared plus 2. But n was an integer. So therefore, n squared plus 2 is also an integer. So yes, it is possible to write it as 5 times an integer. So yep, the sum of the squares of 5 consecutive integers is divisible by 5. Now, remember when you're doing things like this, p, define your p. So direct proofs is what you've been dealing with pretty much since you've been doing proofs. We're now going to look at a different type of proof. This new thing, contraposition, in Latin known as modus tollens, but proof by contraposition. Remember we saw that yesterday. What is that? We said that P implies Q is equivalent to its contrapositive. So not Q implies not P. These are equivalent things. And sometimes it's easier to prove the contrapositive than the actual implication itself. Let's do an example of that. I didn't bother with the truth table because, of course, yesterday we already talked about those being equivalent, so I didn't worry about it with this one. We're going to prove that if 2 to the power of n minus 1 is prime, then n must be prime. Well, I've got to set n up to be a prime number. So I'm going to let n equal p times q. How do I make it a prime number? Then p and q are also going to be natural numbers, but they can't be 1. So neither of those numbers is 1, because if one of them was 1, then n would be a prime number, because that's a prime number. Only factors are 1 and itself. I can write it as 2 factors, neither of which is 1, then I know it's not a prime number. So that's what I've defined, because remember I'm doing the contrapositive here. So I'm starting off saying n is not a prime number. Well, let's have a look at this 2 to the power of n minus 1 then. I now want to show that this is not a prime number, the contrapositive. Going back the other way. So 2 to the power of pq minus 1, which I'll rewrite as 2 to the power of p all to the power of q using our index laws. I can now do a factorisation using that a to the power of n minus b to the power of n idea. So in the first parentheses we match it, so it's going to be 2 to the power of p minus 1. And then in the second one, although I've written it backwards, the power of 2 go down by 1, and then the powers of 1 are going up by 1. So essentially we get 1 plus 2 to the power of p plus 2 to the power of 2p plus 2 to the power of all the way up to q minus 1p. Well, yes, this has now got two factors. Now, p, this first one, is 2 to the power of p minus 1. But I know that can't be 1. Because we said, remember, p is not equal to 1. Therefore, p, if it's a natural number, has to be bigger than 1. So the smallest it could be would be 2. So 2 squared minus 1, smallest it could be would be 3. It can't equal 1. So I know that factor's not 1. Well, let's have a look at q. Well, q is 1 plus 2 to the power of p. Well, I'll just stop there. I mean, it's plus all these other things as well, but as soon as I add something to it, it's not 1 either. So neither of these two factors are 1. Well, I have just shown, or proven, that if n is not a prime number, then 2 to the power of n minus 1 is not prime. That means that if 2 to the power of n minus 1 is prime, then n is prime, and we usually ended up by saying, well, by contraposition. That's why I can say this. I've done the contrapositive here. I can do it by contraposition. Let's have a look at an HSC one from just a couple of years ago. Okay. We had to prove that for all integers, and this time integers bigger than or equal to 3, that if 2 to the power of n minus 1 is prime, then n cannot be an even number. Cannot be an even number. So I want to do the contrapositive. I'm doing this by contraposition. So I'm going to let n be an even number. And we want to negate it. We're saying, well, n is actually going to be an even number. But it's going to be bigger than or equal to 3. So n is equal to 2k, but if it's bigger than or equal to 3, k would have to be bigger than or equal to 2. 4 would be the smallest even number we're dealing with here. Now let's look at this 2 to the power of n minus 1. We want to show that this is not prime. We're doing the contrapositive. We want to show this is not prime. So 2 to the power of n minus 1 would equal 2 to the power of 2k minus 1. Difference of two squares. I've got 2 to the power of k minus 1, 2 to the power of k plus 1. The second factor is not going to equal 1 because again we've got 1 plus something. Is it possible for 2 to the power of k minus 1 to be equal to 1? I certainly know 2 to the power of k plus 1 is bigger than 2 to the power of k minus 1. So again that shows they can't both be 1. And if k is greater than or equal to 2, then 2 to the power of k minus 1 must be greater than or equal to 2 squared minus 1, which equals 3, and because k is bigger than or equal to 2. Well, that means we've got these two factors, and neither of which is 1. Now, if neither are 1, then if n is an even number, that's what I started with, I then concluded 2 to the power of n minus 1 is not prime. Therefore, if 2 to the power of n minus 1 is prime, then n is not even by contraposition. And when we're dealing with primes, contraposition is a good way to go because it's a lot easier to prove something is not a prime number, because I've just got to show neither of the factors can be equal to 1, than it is to try and prove something is a prime number. We have seen this technique before. Proof by contradiction. In Latin, reductio ad impossible. It's what's known as an indirect proof. And here are the conditions for it. If we have the negation of p implies q, right? Because we're going to do it by contradiction. We start off by saying that actually what we're trying to prove is not correct. And if that leads to a situation where we have both R and not R, which is impossible, because remember you can't have it both being true and false. It's got to be one or the other. Right? Then if we have that situation, then that implies P must equal to Q. Okay? Because not P implies Q led to something that was impossible. And so it can't be true, therefore its negation must be true, which would be P implies Q. let's prove this one via the truth table, that this does always come out to be true. So there's all our possibilities, and as I say, well, the R and not R must always be false, because you can't have both R and not R. You can't have that. And I'll fill in the P's and Q's over there, and for P implies Q, we know it ends up with only the true going to false is false. Alright, let's fill in the not. P implies Q, so that's the complement of this one here. So we now have false, true, false, false. If I now fill in, we're working out, inwards out. So I now fill in our implication here. And in that one, the only one that will become false is the one where true implies false. I'm now looking at the green one and the second purple one over here. We've got false implies true, true implies false, false implies true, false implies true. That's always true. Remember, false implies true was okay. That was all to do with sufficiency conditions we talked about. So yeah, this is a logically valid argument doing it this way. Well, let's do some. We're going to prove that the log of 5 base 2 is actually an irrational number. Now, I want to do this by contradiction, so I'll start off by assuming that this is not true. So I'm going to assume the log of 5 base 2 is a rational number. It's not irrational, it's rational. Now, if it's a rational number, then we know we can write it as a fraction, P and Q, where P and Q have no common factors. Right, so we can simplify it down, or a quick way of saying it, they are co-prime. They are co-prime. Okay, well, playing with logs and exponentials, I'll turn it into an exponential equation. 2 to the power of P on Q then would be 5. Alright, well, again, playing with the equation. That means 2 to the power of P must equal 5 to the power of Q. So 2 to the power of P must equal 5 to the power of Q. But hang on, 2 to the power of P must produce an even number, because it's going to be 2 times 2 times 2 times, however many times. But because it's multiplied by 2, it's got to end up with an even number, because all even numbers are divisible by 2. Whereas on the right hand side, we've got 5 to the power of Q. It's going to be 5 times 5 times 5 times 5. It's never going to have a factor of 2. So the right hand side is an odd number. Well, a number can't be both odd and even, and there's your contradiction. We're saying these two things are equal, but hang on, one thing's odd, one thing's even, we have a contradiction. So therefore, what I assumed must be incorrect. Thus, the log of 5 base 2 is irrational. I really should have put down there by contradiction again to explain how I did it, but there's our proof. We're going to prove there are no integers a and b such that we can get 18a, add 6b and get the answer of 1. And remember, integers could be negative, so you might be thinking, oh, well, of course it can't equal 1. But no, use of negative numbers, maybe it's possible. But we're saying no, it's impossible to do it. So I will assume it is possible. I'm going to assume that there does exist these two integers, a and b, such that when I add 18a and 6b together, I get the answer of 1. That's my assumption. All right, well, let's look at this thing. 18a plus 6b, got a common factor of 6. So I'll pull that out and divide it. That therefore means that 3a plus b is 1/6. Hang on a sec. 3a plus b is 1/6. But 3a plus b has to be an integer, because we defined a to be an integer. So 3a is an integer and b is an integer. And 3a plus b then can't equal a 6, because 1/6 is not an integer. There's my contradiction. We're saying it's equal to 1/6, but it has to be an integer. Can't happen. Impossible. There's our contradiction. So therefore my assumption was incorrect. It must be the opposite of that case. So there are no integers a and b such that 18a plus 6b is equal to 1. So the idea is you assume what it is that you're trying to prove is incorrect, and then you try and come up with some contradiction. And then you can turn around and say, but hang on, that's impossible. And if that's impossible, then my assumption must have been incorrect. Therefore, it must be the other case. Let's go back to the 2020 HSC now. In the set of integers, so all integers, P is going to be this proposition. If K plus 1 is divisible by 3, then K cubed plus 1 is also divisible by 3. And it asked us to do a few things. First thing it said was simply prove the proposition is true. Now, they didn't say which technique. You could use any technique you like. I went a direct proof. I think that was the easiest. But I'm going to let K plus 1 equal 3 times P. Because it's divisible by P. But I've got to define everything. So P is going to be integer for all K, which is also an integer. Now I know the factorization for K cubed plus 1 is K plus 1, K squared minus K plus 1. But we just said K plus 1 is 3P. So I could rewrite that as 3P. Well, hang on, I've got a factor of 3. As long as these other two factors are integers, I'm okay. Well, we know P's an integer. We defined it that way. We said P is an integer. We also said K was an integer, so K squared is 1, and K is... So yeah, K squared minus K plus 1 is indeed an integer. So we're good. Right. So if K plus 1 is divisible by 3, K cubed plus 1 must also be divisible by 3. The second part of the question simply said, well, write down the contrapositive of this proposition. So read the thing backwards, but negate each statement. All right. Well, it said, then K plus 1 is divisible by 3. So I'm going to start with that. If K cubed plus 1, but it would have to be is not divisible by 3. We're negating it. The if becomes then. So it was K plus 1 is divisible by 3. It's now going to be then K plus 1 is not divisible by 3. So there's our contrapositive statements that they were looking for. Then the third one. Now write down the converse of the proposition and state, with reasons, whether that converse turns out to be true or false. Because remember we said that the converse of an implication may not necessarily be true if it's true and so on. So is it true or false? Well, here's the converse. Read it backwards. So if K cubed plus 1 is divisible by 3, then K plus 1 is divisible by 3. Wow, it kind of makes sense to do this one by contraposition, because why did they just ask me in part 2 to write that statement down? I may as well use it. Remember, P implies Q is equivalent to the negation of Q implies the negation of P. These are going to be my two statements then. P is K cubed plus 1 is divisible by 3. Q is going to be the statement K plus 1 is divisible by 3. K cubed plus 1, there it is again. There's that factorization we saw before. Now I'm going to play with the second factor here and rewrite it. I'm going to rewrite it as K squared plus 2K plus 1 minus 3K. You see, doing that, I get this perfect square of K plus 1 squared minus 3K. Why did I do that? Well, I know K plus 1 is not divisible by 3. Remember, I'm proving the contraposition. I'm going to say K plus 1 is not divisible by 3. Contraposition if it is not divisible by 3. But then K plus 1 squared can't be divisible by 3 either. Because if I square it, the factor of 3 isn't going to magically appear. Well, if K plus 1 squared is not divisible by 3, but this second term here, 3K, well that's divisible by 3. That means that whole parentheses can't be, there's no common factor to pull out. 3 is in the second one, it's in the 3K, but we just said K plus 1 squared doesn't have a factor of 3. We can't pull it out. So it's not divisible by 3. Well, K plus 1 is not divisible by 3, and that second factor is not divisible by 3. That means the whole thing is not divisible by 3. I can't create this common factor. So I have now proven that if K plus 1 is not divisible by 3, then K cubed plus 1 is not divisible by 3. So by contraposition, I get if K cubed plus 1 is divisible by 3, then K plus 1 is divisible by 3. 2B and 2C, we'll look at different questions from that.